Well, good afternoon, everyone. It's a pleasure to be here with you today. So I'm William Anderegg. I'm a professor in the School of Biological Sciences here at the U, and I direct the Wilkes Center for Climate Science and Policy on campus. We're excited to kick off our set of talks and discussion around the RAI initiative and the environment. And I'm going to just do some opening remarks. Most of what I'll be presenting is really the synthesis of a broad group of folks from across campus, thinking about what are the opportunities and what are the real needs for research and for the University of Utah to engage in this space. So, of course, the background and the context here is that AI could have enormous negative impacts on the environment itself. These are both direct impacts for the costs of running AI, of power and water and data centers, and the greenhouse gas emissions and water costs that can come from that. And then some of the indirect challenges of misinformation, polarization, and increasing inequities. At the same time, there's another set of opportunities that AI can help us tackle environmental problems in thinking about forecasting of risks and early warning systems, and I'll talk more about each of these in a little more depth. And then thinking about the deployment and scaling of some of our most promising solutions to rapid environmental change like climate change. I think our take home here is that we urgently need engagement from across disciplines to tackle these areas and really engage with some of the regulation, governance, and policy in order to avoid some of these top harms and maximize and really supercharge some of these opportunities. So this is the group that came together. I know some folks are in the audience today, and this was a really broad group from humanities to health sciences to climate sciences and engineering. And our goal of this working group was really to put together a vision and a mission about responsibly developing and using AI to address these human environmental challenges across scales in a way that promotes resilience and fosters sustainable development. And within that, our goal was to think about what are some of the focal areas that the University of Utah could lead on, and what are some of the use cases that we should be thinking about AI and studying AI itself in the environment. This is, in essence, just the overview of the process that this group went through, sourcing ideas from units across campus, and with really highlighting some of these high-level points to leverage some of the strengths at the University of Utah to promote and build an AI-savvy workforce, and to emphasize multidisciplinary research that centers responsible AI development and assessment of potential impacts, risks, and harms. And the key point of this is a key element of responsible is studying AI itself and not simply just applying AI. That applied AI is different from responsible AI. So our two, we think, the exciting opportunities here for the University of Utah to engage on are these two focal areas of developing sustainable AI. So thinking about how we develop AI in a manner that minimizes its environmental impact and maximizes long-term sustainability, and then harnessing AI for environmental resilience challenges. And we'll dig into some of those use cases for each of these. On the sustainable AI piece, I think this is really both thinking about very proactively and doing research on the governance, ethics, and regulation pieces, particularly relating to AI and the environment. It's looking at and assessing and doing audits of the potential environmental impacts of AI, the costs of running and training AI models for energy, water, and minerals, and potentially how it has these indirect set of effects as well. And then someone thinking of these indirect AI society interactions. And this is where it really bridges across many disciplines into the social sciences, into the humanities, into the health sciences around AI and misinformation, political polarization, and how it affects our ability to tackle environmental challenges. Flipping then to this second set of focal areas and use cases, we think there's a lot of exciting potential for AI to advance environmental resilience, and this is maybe tools to improve models of climate and air quality, improving observational data sets, and then accelerating some of these climate solutions, like optimal deployment of different climate solution pathways, whether that's nature-based climate solutions or renewable energy, uh, informing net zero plans for companies and governments. Third general bucket is really around this risk management, risk detection, and risk forecasting or early warning systems. These might be rapid wildfire response systems or detecting deforestation in forests in order to take action quite rapidly. And then the final section is really thinking about how can AI as a set of models and approaches help us understand and more proactively plan out our future growth challenges and fine-scale human population dynamics, land use change and planning, and these sort of future scenario mapping for more sustainable and more resilient societies. I want to give you one exciting example of one of these. This is a new scholar who will be coming to the University of Utah soon as part of a cluster hire led by the Wilkes Center for Climate Science and Policy, named Makoto Kelp. And what Makoto does, and hopefully he'll be here in a year to talk to you all and share some of this, is he pulls in a lot of these AI tools into really complex air quality models and uses the AI, that these are models are incredibly powerful, but also incredibly computationally intensive and slow. And this limits our ability to do a lot of really rapid detection and modeling of air quality and of things like wildfire smoke. And so what Makoto has done is built a lot of physics emulators with AI in these air quality models. And he's using them to understand where should we be placing sensors to monitor air quality carefully? Where should we be monitoring air quality from fires in the Western US and prescribe burns? And how does this, who might be exposed to the smoke from both prescribed burns and wildfires in the Western US? So these are some of the, just a quick flavor of some of the exciting ways that I think you can bring some of these tools to bear for environmental resilience. And then finally, I want to leave with a couple notes on how can we maximize and really synergize to advance the University of Utah's impact. And our group spent a long time thinking about what are the different groups and centers and hubs of excellence around campus that something like the RAI initiative could amplify, could connect, and could leverage. There are a number of environmental focused centers, the Wilkes Center, the Global Change and Sustainability Center. There's some recent newly launched centers as well, the Wired Center on Grid Resilience and the Southwest Sustainability Innovation Engine that are, I think, really nicely set up to interface with RAI and to team up to work together to advance this goal of environmental resilience and sustainable AI. Also, we'll have a session this afternoon about health, but I think there are a huge amount of intersections between the environment and health. We were just talking about air quality and smoke as a prominent example, but many, many others that we'd like to see a lot of interaction between environment, health, and the education pieces in this RAI initiative. And with that, we'll turn it over to our next speakers. Thank you so much.
Hi, I'm Isabel Freiling. I'm an assistant professor in the Department of Communication in the College of Humanities and also a faculty affiliate at the Global Change and Sustainability Center. And my work is on science communication, also political communication, which often plays a role with many of the science topics. And today I want to talk about AI's role in misinformation. And that, of course, can be diverse. Like if we look at the algorithmic display of content, very helpful. Otherwise, we would have an information overload with everything that's out there. We need this relevance sorting for us, but also that can have negative consequences when we don't see as diverse content as we would like to see. And for generative AI, that can be helpful when people chat with a generative AI tool about some potential misinformation they've encountered to figure out if this is actually false. But of course, generative AI could also create that false information. So there's up and downsides to both of those. And my talk is based on this paper that I wrote with a few colleagues on how we can better understand misinformation and then applies it to the AI context. So first of all, should we intervene with AI against misinformation? To figure that out, we have a lot of misinformation research that is done in labs or in online experiments where we show people content. They know they are part of the study, pay a lot of attention to our content because they are in the study and want to help us, and then they give us an answer to follow-up questions, meaning they pay much more attention to the content we show them in our studies than they would do in the real world. Then we have to ask ourselves, how well would these interventions that we're testing actually then work when people pay less attention to the content in the real world? Do they work the same way? Should we use AI to fact check content? And also, it's often much harder to define the accuracy of content in the real world because we can have a message that contains of so many different claims. Some of them might be true, some of them might be false. Maybe there's even a claim partly true, partly false. So it's not as clear as the claims that people are usually testing in their research to examine the influence of misinformation and how well interventions work. And this is also complicated by uncertainties that are inherent to the science, to sociopolitical climates, and to the media systems, which introduce error in how we can assess the accuracy. This is an example from factcheck.org where they were answering a question on wind energy's key environmental advantage. And I wanted to point out the full answer start here, where they say a genre of lengthy posts on social media claims to poke holes in measures designed to reduce greenhouse gas emissions and mitigate climate change. The posts throw out numerous statistics without citations, making it difficult to quickly sort fact from fiction. They looked at posts like this one, where you can see it's very long. There's so many different claims in there. Some of them might be true, some of them are false. But in the end, like, what do we do with this whole message? Do we want AI to intervene here, and how? Picking a certain claim or trying to correct the whole message. So it's just not that clear. And we also need a better understanding of misinformation and how harmful it is in the real world to actually then decide if it makes sense to intervene. So how can we inform productive pathways for the misinformation research, but also practice? We need to consider the ecosystem in which the information, but also misinformation is evolving, and then assess the accuracy of the claim or the threat of the claim, which is complicated by the intersecting distortions that come from the nature of the science, the sociopolitical climates, and the media system. And I will go further into these on the next slide. But basically, those distortions introduce error and thus uncertainty and variability, which can really influence the costs of misinformation interventions. And uncertainty types and their attributes for scientific truth claims, which could be about AI, right? Can be in the scientific area about how attainable is our knowledge on the science, how fluid is the evidence, so where are we in the scientific process, how much do we know about the topic already? you all know how the scientific process works with, well, we do more research, we get closer to the truth, and some of the early studies will turn out false. Then on the socio-political side, we have, for example, the associated harm with a message. So is it actually going to do harm, or will people not really do anything based on seeing that message? How acceptable is source error? So if a message was created by generative AI, how much error needs to be in that message for us to call it misinformation? Does that differ if the message would come from a scientist communicating about their science? Do we think if the scientist makes one mistake, it's misinformation? Is that maybe different for AI? And on the distributional side, we have elite salience where we have political elites on social media, influencers, for example, sharing messages, and then many more people see that and engage with it because of those elites sharing it. Or the algorithmic traction a message is getting because of other factors that can be how emotional the message is. So how likely is it to create engagement, and thus the algorithms would prioritize it to keep engagement on their platform. And knowing all this, should we better do something against misinformation? I would say not in every case, because intervening can have negative consequences. One of them is that there can be a backfire effect if you fact check something. So assume someone has heard the information, then sees the fact check that tells you this information was wrong and this part of the information is correct. Then in that situation, they might be like, oh yeah, she just told me this part is what's correct, so I know now. But later on, when some time has passed, you have heard the misinformation twice, maybe even more times, and the correct information less, maybe one time, right? And so later on, you will remember what you've heard several times. And that might not necessarily then be that you remember about the information that was false. You might just remember that piece of information. So repeating something false can make it stick in people's minds. Then we see some bias accusation against science. A prominent example was LancetGate with the Lancet retracting an early COVID study, and then Trump supporters claiming that they're biased political attacks by the Lancet and the medical community more broadly. So it can also have political effects. And based on the attributes of claims that I've just talked about, the claims can also be elevated because the attributes are variable. They're not just dichotomous. So it's not that the fluidity of evidence is either high or low. It can be like somewhere in between, for example. And these different attributes I've just shown you are not equally relevant for each claim we come across. And these all intersect and interact. And I want to show you an example of how this can look like. So I have this claim, wind kills all the birds, made by Donald Trump in an interview that was streamed online. But then also the Harris campaign picked it up, posted about it, probably to show, hey, he made this claim. And when we look at some of these attributes, the fluidity of evidence that wind kills all the birds is very low. Wind kills some birds, but also many, many more birds die in other instances. The elite salience here is very high because it was first voiced by Donald Trump, then also picked up by liberal elites in an election campaign. And there might be different standards of evaluation. So maybe for policy actors or politicians, we're like, maybe this is par for the course for Donald Trump. If this was voiced by a scientist, for example, this would probably not be par for the course. And if we look at the algorithmic traction here, it's rather high. partly due to this elite salience that really shared it more broadly. And let me see how much time I have. Do I still have time? 1 minute, okay. Another quick example where we see all these factors are very low is the Earth is flat, right? So we can then decide, do we want to intervene against the Earth is flat? Do we feel like we need to intervene more here? Does it make a difference? Will it cause much harm? And do we want to leave those decisions up to AI? Or because it's much more complex and it's probably easy to not that easy to evaluate how these attributes would pan out. So if we use AI to intervene, we should account for the sources of distortion that I've talked about, and then intervene for the claims that are actually dangerous. And thinking about those attributes can help us to intervene, focusing specifically on the factors that make the claim dangerous, because not all of the factors might make it that dangerous. All right, thank you.
Hi, I'm Derek Mallia. So I'm a research assistant professor at the University of Utah's Department of Atmospheric Science. Big disclaimer, I'm not an AI or machine learning expert. I'm just an atmospheric scientist that's trying to figure out how to use AI and machine learning for some of the forecasting applications that I am working on. So just to give you a context of some of the work that I'm doing, so basically I'm working on issues related to the forecasting of wildfires and then the byproduct of wildfires, which in this case will be wildfire smoke. And this is because large wildfires are essentially degrading our air quality across the summer, and these effects are becoming more widespread. And so we're not just seeing smoke across the Western US, but we're also seeing this in parts of like, New York, for example, areas that you traditionally don't see a lot of wildfire smoke. And so this is definitely a big growing concern. And these trends are expected to continue as a result of climate change. And it's worth noting that, when people think of the atmosphere and weather and so on, you think of hurricanes, tornadoes, and so on, but it's actually poor air quality that's one of the biggest causes of mortality, where wildfire, or for air quality, it's estimated that mortality is on the order of 100,000 per year, while if you combine other natural hazards together, it's going to be less than 900. So air quality is a really big issue. You can't always see it. Sometimes you can, especially in the case of wildfire smoke. But nonetheless, it's a really big problem. And so along those lines, when we try to forecast hurricanes, tornadoes, things of that nature, we have weather forecast models that can do that. But in terms of forecasting wildfire smoke, a lot of that work is still kind of at the beginning stages. We didn't really have our first weather forecast model that could actually forecast smoke until about 2016. So this aspect of weather forecasting is kind of lagging behind. And so these are just, some of the things that I'm working on are kind of the problems I'm working on is how can we better forecast wildfire smoke? And so unlike traditional weather phenomena, the state of smoke forecasting is, as I mentioned before, it's underdeveloped. And part of that has to do with the fact that wildfire and smoke forecasting is really, really difficult in that first you have to get the weather forecast correct, which is already kind of a difficult proposition. And then after you've gotten the correct weather forecast, then you have to make that fire forecast. And then that will kind of feed back into the amount of smoke that's being produced and how that is carried downwind. So long story short, you have to basically forecast the kind of fire growth at the surface. And then along those lines, then that heat basically causes the air to rise over the fire, carries the smoke upwards, and then lofts it kind of downwind. And there's a lot of really kind of complicated physical processes that kind of interact, that kind of drive this downwind dispersion of smoke. And so the big issue is with especially wildfire smoke plumes is that there's not really a lot of data on them. You have satellite data, but it's usually just providing a snapshot of the smoke from the very top. It doesn't really tell you about the 3D structure of smoke. So there just aren't a lot of data sets out there to really tell you a whole lot about smoke plumes. And so along those lines, with this kind of limited kind of data sets that we have, we can't really just machine learning or AI our way out of the smoke forecasting problem. It is worth noting that I think there's a lot of places where AI machine learning could be used, but I think we're going to have to take more of kind of a hybrid approach. I think this is a case where you have to have the physics-based approach and machine learning kind of working together to kind of tackle this really complicated problem. And so some of the work that we're doing here at the University of Utah, so this is a joint effort between Kai Wilmot, who's a postdoc that's working under me, along with Heather Holmes, who's a professor in chemical engineering. And so we've been developing this kind of air quality and smoke forecasting framework. And something that's really novel about this is that in addition to our kind of smoke forecasting framework that you see right here, we actually also tried to forecast the fire because as of right now, most weather prediction models assume that, okay, if you have a fire, how it's burning today is how it'll burn tomorrow. And we know that fires actually change quite frequently in terms of their intensity over the course of a couple of days. And so we've actually incorporated kind of a fire forecasting algorithm within our kind of smoke forecasting framework to tackle this really kind of complex problem. And then that gets fed into the plume rise model, which lofts up the smoke, and then the smoke then gets carried kind of downwind. But as I said before, the fire activity component, that is something that is not really implemented in any forecasting framework as of right now, and something that we are working on right now, which is really exciting. It's worth noting that AI machine learning is actually being used in some cases to produce regional weather forecasts. So a lot of these models are kind of running at a coarser scale, but these kind of AI approaches especially can reproduce weather phenomena, especially at the larger scales, which is really encouraging. Um, Satellite data is another really good place to kind of try to use AI in the sense that satellite detections are often very noisy, and especially in the context of fires. You know, we have basically pixels, but we know that fires aren't actually pixels, but they are actually, they have, you know, discrete kind of perimeters and so on. And so you have to kind of employ kind of really sophisticated data assimilation methods to kind of reconstruct a perimeter from those satellite detections. And then, you know, right now we're kind of running a physics-based approach for the fire activity forecasting, but even that approach has its limitations. For example, it doesn't really perform that well for the southwestern U.S. I think it's related to the density of the vegetation down there, but nonetheless, I think this is also a really good place where we can implement machine learning and AI. And so this is kind of like the perspective from that satellites, for example. So here, this is what a large wildfire might look like on satellite. So it's just a bunch of collection of pixels. And you usually get these like every 8 or so hours, depending on the satellite that these pixels are coming from. Most of the satellites are polar orbiting, and so they get limited snapshots. And so one thing that we did, and this is conjunction with my colleagues at San Jose State University, is we took these pixels and then tried to reconstruct the fire progression history, and then we kind of fed that into our air quality forecast model. And so we've used this for air quality applications. So one thing that my graduate student has been working on is trying to determine how wildfire smoke is going to impact ozone, which is another atmospheric pollutant, very complex and difficult to model. But one thing that we found is that, you know, in terms of ozone, you know, big driver of ozone is thought to be anthropogenic emissions. But we found that actually wildfire smoke can generate a lot of ozone through secondary formation. And along those lines, you know, usually the thought was that you would have to have a wildfire plume that would move over an anthropogenic or human emission source to actually create ozone. And this kind of research kind of showed that that's actually not the case. Why I'm showing this as it relates to machine learning is machine learning actually helped us kind of constrain those smoke emissions. So we're actually accurately resolving how much smoke we're actually are emitting from the fire so we can get kind of an accurate simulation. Another thing I think that machine learning could be used for in AI along those lines is, you know, we could use archive fire progression history from those satellite detections. And what we could do there is use this as a training database for basically creating a new fire spread model or new fire activity model that can basically forecast fire activity out to 5 days. And so that is another thing that we'll be working on. This is a future project. I've actually started working on this. Might use like a random forest or gradient boosting method. That's still TBD though. I don't know if we'll have actually a big enough sample size to use neural networks. That's also TBD, but I'm still trying to figure that out. And then also this kind of smoke forecasting framework that we've been using will be also used for science field campaigns based on trying to figure out the likelihood of the initiation of a thunderstorm generated wildfire. And so this is another thing that we're working on. So we call this the probability of a pyrocumulonimbus cloud. And this is another kind of application. So, over fires, sometimes if you get big enough fire, you can actually create a thunderstorm over that fire. And that can be very treacherous for fire managers in that if you have a thunderstorm that blows up over the fire, it can create a lot of erratic winds that can actually blow the fire around and makes that fire very treacherous to kind of fight if you're a fire manager. And then, we have this kind of smoke forecast that's actually automated and running right now. So we actually ran this model for, or did a forecast for September 11th. And so this is just kind of that forecast where you can see, this was like, what, 2 weeks ago or a week ago? I forgot how long ago it was. We've gotten a lot of smoke, but yeah, you can see that we got this kind of Smokezilla event, as I would like to say. I would say my second worst air quality day that I've seen here in Salt Lake City, and I've been here for over 10 years. But yeah, our model was actually able to kind of forecast that event, which was really, really exciting. And then we were able to forecast this out 2 to 3 days in advance, which is really, really exciting. So yeah.
Excellent. Let's open it up for questions at the.
You can go ahead.
Oh, okay.
Sorry. Saw your hand first.
I was first. So, yeah, a question for Isabel. So, a lot of AI platforms, apart from Microsoft Copilot, own prompt that users put in to generate an answer. A lot of these prompts include scenarios, like as an example. Is there any data to what extent this scenario feed in AI hallucination? And do you foresee a scenario when targeted disinformation via prompts could be used to mess up particular AI system? Thank you.
Yeah, so first of all, I am not working like on the AI science part of it. But I mean, keeping those prompts, if you have a disinformation campaign that you want to get out, like that can be so helpful to make that effective. And it's incredibly dangerous in that sense, right? Because people might give you some ideas of like, what are the crucial passages in the information that made them either question it or which parts did they not question. So you could probably analyze that in a sense of what or how do we need to structure a message that it will not raise skepticism among people so that they will believe it more, right? So if you wanted to use it for that way, and those prompts are kept by many of the AI tools, I think that is some danger, although we hope they keep the data safe in that sense. But that's like where my expertise ends on what they actually do with the data and how safe the prompts are. But if you think of it for using it in disinformation campaigns, very dangerous. And then on the other hand, of course, if we were using this for doing good, we could try to analyze those prompts to see, okay, what are the parts that made people skeptic about this message, right? So can we then put information out there about, oh, if a post contains this, it's likely to be misinformation. Or be careful when you see something containing this type of language, image, whatever, it could be false, just to make people more aware of it. That's the other way it could be used.
Thanks for these presentations. a theme that I was noticing in all of them is the common tension between trying to predict the things that we can actually measure and being able to do something about the things that we care about, right? So in some sense, do we really care about particulates, or do we care about human health and the impacts on our infrastructure? Do we care about lies online, or do we care about the changes in people's psychology and the cultural impacts? So I'm just curious, in each of your work, how do you sort of wrestle with and try to reconcile that tension between here's the stuff we can measure, and so therefore it's amenable to prediction, versus the things that perhaps impact human lives?
Yeah, I can. Yeah, so that's a great question. And so yeah, I guess as a scientist, like I focus on the particulates, and that's usually because as a forecaster, that's what I'm verifying my data against. So I think when you're trying to actually link that to, like, let's say human health, like those linkages are more difficult. So I think as a scientist, and given how far at least smoke is in terms of smoke forecasting, kind of it's at its beginning stages. Right now, I'm kind of more focused on the particulates themselves and comparing that with the data that we have. But now that it looks like the model is behaving as we want, or as we're hoping, now we can start transitioning these to more advanced applications, like relating it to human health. And so I look at the smoke forecasting thing. I mean, intellectually, kind of stimulates me from as a scientist, but what can we use? A smoke forecast model. Why do we actually need that? And so we know that indoor air quality, depending on where you are, is usually better. And so if we can give warnings to people to get inside or to stay inside, if that's actually possible, that's like the kind of or the kind of applications that these models could be used for. So.
I would just add, I think this is where the multidisciplinary approach is incredibly powerful, right? That each of us has our own specialties and tools, but we can collaborate with a bunch of health sciences folks, which the U has an incredible research community here, to make those linkages between smoke and then the health impacts. And it does get, sort of harder and harder as you move along this chain of evidence and across different fields and across different spatial and temporal timescales. But we know that smoke puts people in the hospital and exacerbates children's asthma. We know plenty about the health impacts. And so this is where this multidisciplinary approach, I think, can help better connect that. And I see that especially in some of these kind of air quality, climate extremes, and some of these events like wildfires as being one of the huge opportunities that the University of Utah could be really one of the foremost places in connecting those dots.
So your question is actually something I've been thinking about a lot. It might have come through in my talk that when I was talking about let's do something about the misinformation if we think it's actually harmful. Otherwise, we might just be wasting our efforts. We might make it worse. So in that sense, I've been thinking about it a lot, but also when we look at a lot of communication research that is about how people make sense of information, for example, that they encounter somewhere online, on social media, etc. A lot of that research is done with like measures and designs in how we set up our studies that use what's available to us. So like we can do that study, but it doesn't always get to the real world problem. And a big issue I see for like social media related data is because there is so much algorithms going on in like deciding what we see. You might see a post on social media that is never shown to me. You might have seen it when it was just posted by someone. The person sitting next to you might have seen it a day later with like so many more comments and likes on it, which gives you then maybe a completely different picture of that post. And we oftentimes in our research just do not have access to that data. We don't know who saw what and when. And so in our experiments, we're using some posts that we show people and then look at how they pay attention to the post when we show it to them, which might not happen that way on social media at all. Or some other approaches are developing a fictive social media platform that then uses some algorithms we think are working on the social media platforms that people actually use. And so it's all like this type of proxy research design that we use because we have to. But the bigger issue is that we don't have access to the data we would need to do those studies. And we need to work on that. Like some research where academics partner with, for example, social media platforms, they have access to that data, but then they are not allowed to share it. No one else can replicate it. It's a huge issue.
Isabel, please keep the mic. I wanted to ask you, in the type of research that you're doing, when you're thinking about fact-checking certain posts, is there a second-hand effect that is perhaps unintentional of giving credibility to posts that you decided not to fact check? So people see that there's no red flag there and therefore assume, okay, yesterday it went viral that all birds get killed by wind. That was fact checked. Today somebody posts birds don't exist. That doesn't get fact checked, so this must be true.
I can see the point for very viral posts where we fear that people actually believe in them. But for many of the posts we see out there, there's just no fact check. And that can be for many reasons. It can be that fact checkers just did not deal with that post. It doesn't mean that it was never fact checked, right? So in that sense, it's not that a post that doesn't have a label that this is fact checked then automatically means it's true information, right? I mean, we could probably award like a badge, a flag, or whatever to a post that has been fact-checked and has turned out correct. But the absence of it really, because there's so much information out there and not everything can even be fact-checked, if we just use human fact-checkers, of course, that wouldn't necessarily mean that it's automatically true.
I have a personal comment about the predictive element of the fire and the direction and also the smoke. Is we have a place in Montana. I have a hybrid position and I'm there a lot. And so we care, we look at the fire maps all the time. And we did enjoy that mega fire event that you showed, all that smoke. Anyway, so it's important for our ranchers. They're very sophisticated and they do look at this stuff. And I want to know, how can we promote that this is available? I think we have fire jumpers. I live in the Flint Creek Valley area, and the fire jumpers they will congregate there when there are fires in our area. And so I'm super glad that they're there, and we haven't had any trouble. We haven't had a fire come near our home in a long time. But I'm thinking of the livestock, and if I were a rancher, I could move my livestock depending on how thick the smoke is and how big my ranch is. All that is so very important, and I thank you for doing that work. So I'm just curious, how do you promote more about this to other outlets that can pick up this information and move it forward?
Yeah, so I think the good news is that, with the smoke forecast model that we're developing, that is something that we're working with the Wilkes Center, for example, to get that data out there. And so, but even then, I think that there's still more work to be done in the sense that, first we want to make sure that the model is working, which, it seems like it is actually working. So I think we're feeling pretty confident about the results. But I think one thing that I think a lot of scientists struggle, even myself, is, okay, how do we get, information about particular matter? How do we get that information to the everyday user of, like, what does that actually mean? And so, one thing I do is I ask my wife, who's a music teacher, okay, here's the map of smoke. If she can understand it, then I need to rethink about how I'm actually conveying the information I'm giving. So along those lines, I think, part of it is, of course, getting the data out there and on a user-friendly webpage, for example. But I also think displaying the data in units that people can actually understand and actually can take action on. And so I think that's another really important kind of step to that, and disseminating that information.
I think that's also where science communication can come in. Because in science communication, we look at what people think about certain issues, what part of the issue they care about, and knowing how people make sense of information, we know it's not that they just need to see the information and will actually immediately do what's in that information and follow the science or whatever. But we need to make it relevant to them. And so we can, for example, find out in a survey what people think about wildfires, how that relates to them. And since you've mentioned it can help save livestock, we could, if we wanted to reach people who have livestock, specifically focus on that it can be used for that. That can be very helpful, which is something that they care about. And so they would be much more likely to listen to what we have to say about the science and to look at the model and use it for that, because we've outlined, hey, this is how it's relevant for you.
So this David Greaves with Summit V. I'm curious, so under the current conditions, how is AI, or how are you using AI today? And how do you anticipate AI helping you moving forward or in the future?
Yeah, so I think the big thing is I think there's a lot of uses for AI for satellite fire detection. So I just think that when you have like an image of a fire from a satellite, it's very pixelated and so on, and trying to actually figure out where exactly the fire is growing. In addition to that, you actually need to know what the fires burned previously, because the smoke that was emitted from the fire yesterday actually is still, it's being transported through the atmosphere, and maybe it's like halfway to, like, let's say New York. It's a very crude example. So, one thing that we're really looking into is, can we use satellite to make these fire these fire progression maps, so we can kind of get a sense of what the fire's emitted now and what it's emitted in the past, and then seeing if that actually improves forecast. So that is, I think, at least for the smoke forecasting context, that is the lowest hanging fruit. And I think the other thing is fire activity forecasting. We're using models from the 1970s. They're based on empirical models, based on lab experiments. And I think with all the great satellite data we have, and the fact that we can kind of build out fire progression maps, that some type of machine learning algorithm could probably be used, or AI method could be used to just create a new kind of parameterization that can kind of better forecast how the fire is going to spread in the future. So that's my very, I guess, selfish use of how I would use AI or machine learning.
I'd say briefly, we use it certainly in the near-term forecasting of fires and droughts and forest disturbances. How I think about it is, where are the areas where we have huge amounts of data and it's really hard to sort through it with traditional methods. The sort of pattern detection and extracting clear patterns across massive amounts of data in the environment, it's satellites, it's climate data, it's maybe some of the kind of Internet of Things type data, but it really is, I think satellites are the biggest opportunity there.
Going back to David's question in the beginning, right? AI allows you to take this meta view. You can find relationships between different phenomena that make part of it. For example, the impact of the air quality on, say, people turning up at the ER or other things. So how do you create that data-driven part of it with the typical physics-based and other models, right? How do you create the bigger correlations? And that's where AI can help. And that goes back to the point made around the multidisciplinary collaborations that are essential around that AI.